Okay, moving on to 3 dimensions in our vectors. Very similar to 2 dimensions, just adding on an extra component onto it. So before, I had x and y axes, which corresponded to unit vectors I and j. Now I'm simply adding on a z component or a k unit vector. Okay. Now, as we move forward, just note at this point, we'll talk more about this later, that the orientation of these axes have to be in this way. I mean, it can be rotated certain directions, but the positive x, positive y, positive z all have to be in that orientation relative to one another. Again, you can rotate it one way, but again, they have to be in that relative orientation. And we'll talk much more about that when we talk about the right-hand rule as it pertains to moments. But for now, just remember that's how it has to be. Once I have those set up, really, I can break up my A vector that I have right here into the x component, y component, and z component, just like I did in 2 dimensions, and write that vector as axi plus ayj plus azk. This is exactly the same as 2 dimensions. It's just got this third component on the end of it, the z component, that I have to include as well. Okay, but nothing conceptually new here. Okay. Now, in order to find the magnitude of it, really nothing conceptually new here. It's still just Pythagorean theorem. But in 3 dimensions, I have to do a little bit of extra work here. Okay. So if I look down here, I've got 2 right triangles. I've got this gray right triangle that is laying on the xy plane. And then I have this vertical blue right triangle. And they share this side right here, this A prime side. And that A prime, if I look at the gray rectangle, is the hypotenuse. So it would just be ax squared plus ay squared square root to find the length of this side. Okay. Now, this side and this side, okay, sum up to the hypotenuse on this light blue triangle. So to find the hypotenuse, which is the magnitude of the vector of interest, that's just going to be a prime squared plus az squared, the length of this side and the length of this guy. Well, plugging in what I know about a prime squared, this magnitude a is simply ax squared plus ay squared plus az squared. And that's Pythagorean theorem in 3 dimensions. I oftentimes refer to it as square root of the sum of the squares because that's what holds true in 2 dimensions, 3 dimensions, and really mathematically 4 or 5 infinite number of dimensions. We'll never go more than 3 dimensions. I call it square root of the sum of squares. That's how we find the magnitude of any vector. Okay. Now, these coordinate direction angles I really don't like. I actually prefer you use this notation when writing a 3-dimensional vector. I get more from this than I do from the coordinate direction angles. However, you should know what coordinate direction angles are, knowing that moving forward I won't use them very much, if at all. Okay, and what coordinate direction angles are if I have my A vector, it's the direct angle between the x-axis, the positive x-axis, and that angle. So alpha goes from the x-axis to A, beta goes from the positive y-axis to A, and gamma goes from the positive z-axis to A. Now I've got these right triangles here. Okay, that's a adjacent angle to the y, adjacent angle to the x, adjacent angle to the z. Okay, so I use cosine in order to find these angles. So cosine of alpha is ax over a, cosine of beta is ay over a, cosine of gamma is az over a, where a again is the magnitude of the total vector, and these are the components of each. Again, I'm not a big fan of these because those angles are really hard to conceptualize and visualize, whereas the ax, ay, az I think is actually easier for you to kind of figure out what direction the vector is going in. But that is, if it asks for coordinate direction angles, that's how you find them. And that's just how you can define angles in 3 dimensions. In 2 dimensions, those angles make a lot of sense. In 3 dimensions, it makes it a little challenging. Okay. Now, addition of these vectors works exactly the same as 2 dimensions. Again, I'm just adding this final term on here. So when adding these vectors, I'm going to sum up all the x components, sum up all the y components, and now I'll sum up all the z components, okay, to get that resultant vector. Exact same procedure, just a 3rd dimension.